Hello, everybody. Hey, this is going to be our next lecture, and it's going to be on vectors. And this is essentially chapter 3. This is what we need the basic background in order to do chapter 4, which is kinetic equations or motion, velocity, acceleration in 2 dimensions. So we need to talk about this. All right. So a vector. What is a vector, guys? Okay, it's going to be a measurement, which is going to have a number, a unit, and a direction. Okay, so a scalar is just going to be a measurement, which is going to have a number and a unit, okay, but not a direction. Okay, and there was a kind of a shorter video last week about scalars and vectors. So essentially what we're going to do is we're going to get to the analytical. We're going to get to the analytical portion of what vectors are. Okay, so anatomy, the anatomy of a vector. Okay, and we're going to do so a vector has 2 parts. Okay, it's going to have the tail and it's going to have the head. Okay, the length of the vector, the length is equal to the magnitude or number of the measurement. Okay, so it's essentially that part right there. Okay, the direction, okay, the direction is just whatever direction it's going. Okay, and in this case, horizontally to the right. Now, I specifically made this 25 centimeters long. Okay, now even though I made it 25 centimeters long, I'm not going to call it centimeters. I'm going to call it meters per second. Meters per second. Doesn't matter. Now, the length of the vector is proportional to whatever vector it is. Now, unless we have a second vector, it doesn't really matter the length of the first one. We could call it whatever we want. Okay? And you guys, what we're really talking about here, we're going to call this essentially the graphic part of a vector. And we're going to see that very often the graphic part of using vectors is a really good way to get an idea about your final answer. Then in the second part of this video, we're going to talk about the analytical part of our vector. And that is going to give us a more precise way of determining answers when we do calculations. So this is kind of that check, that we have. All right, so if we have another vector, and let's just say that this vector is just this vector right here. Let's make it a little bit longer. Okay, we're going to make this that is 20. That's 20 centimeters long. Okay, but what I'm using it in terms of measuring a velocity vector. So it's really 20 meters per second. What direction is that purple vector going? Well, it's going this way, right? Okay, so what we can do here is pick up vectors. We can pick up vectors and move them as long as we don't change their length or change their direction. Okay, so I'm going to pick up this one, and I am going to draw it. Okay, so we'll call that vector A. Okay, you guys see that little arrow over the V there for vector A? That is indicating that it is a vector. Now, it's pretty obvious there, okay? And now I'm going to add to that this vector B, So vector A plus vector B is equal to the resultant vector, okay? Okay, so that's the resultant vector. And the way we do that graphically, is we're going to connect the tail of the first one to the tail, or to the head of the second one. Okay, so when you are so this was vector A, and this is vector B, and this right here is the resultant vector. Okay, so how long is that vector? Okay, well, we can measure this vector, and we know it's 25 centimeters long, which corresponds to 25 meters per second. We know that this one is 20, which corresponds to 20 meters per second. Now, graphically, we can just measure it here, and we can say that it is 41 centimeters long. Okay, so this resultant vector is equal to 41 meters per second. So if we had a vector that went this way going 25 and this way going 20, it's going to add up to be 41 going in that direction. Okay, so if we had this and then we added, let's say we added a vector that was 40 centimeters long this way, which again would be meters per second, and then we added one that was 30 meters per second that way. Now, if we added all four of those vectors together, okay, then what would be the resultant vector? Okay, so we can keep adding them on, and now if we measure the distance from here to here, then we can get our total velocity vector. So that would be from here to here, and that would be about 28, and it would be in this direction. Okay, so if these were meters, right, and you walked 25 meters this way, and then 20 meters this way, and then 40 meters this way, and 30 meters this way, how far would you be from your original spot? And the answer would be 28. Okay, so any sort of vector quantity, if you have multiple vectors, you can add them up in this way. Does that make sense? Okay, easy peasy part. Now we're going to get to the analytical part. So you guys, I'm going to go back to just adding vector A and vector B together. Okay, Now, vector A, okay? Vector A is equal to 25 in the x direction and plus 0 in the y direction. Would you guys agree with that? Okay. And then vector B is going to equal to how far is vector B in the x direction and how far is it in the y direction? Okay. It is going to be 14.1x plus 14.1y. Okay. So, you guys, what would you say the angle was right there? If you had to guess, what's the angle there?
60.
I
45.
I was shooting for 45, right? But I didn't measure it. Okay. If it was 45, okay, and I know the hypotenuse is 20, then how am I going to determine the x value and the y value? We're going to use trig, okay? So if I said 20 sine 45, that's going to give me 14.1. Now, if I said 20 cosine 45, it's going to be 14.1. Now, they happen to be the same because they're at 45 degrees, and you know that the sine and cosine are the same for that, okay? And therefore, we're going to get the x component and the y component, okay? And the x component is really going to be the cosine, and the y component is really going to be the sine, right? From this orientation, okay? So now, if we add these two together, and this is the beauty of adding these up, is we can say that this is 39.1x plus 14.1y. You guys see that we're just going to line them up and add them together. Okay, so this right here is our resultant vector. Except we don't call x, x. We call it I. So these x's are i's. And our y's are j's. And if we were to have a z, the z-axis, that would be called k. Okay, so we're going to have I, j, k is just the same as x, y, and z. So why do they do that? To distinguish between a scalar and a vector. So if you have an x direction, that could be a scalar. So if you had an I direction, you know that is a vector. Okay? So, but you guys don't let that throw you off. Just think of i's as x's, j's as the y's. I's, x's, j's are the y's, and then the z would be the k's, right? So just think of it that way, and it will be all the same. All right, so now what is the length? You guys, what is the length of this vector right there? If we know that this length right here is 39.1, and we know that this length is 14.1, then what is this length? And we're just going to use the Pythagorean theorem. So we're going to say that the length is going to be 39.1 squared plus 14.1 squared. And then we're going to take the square root of that. Did you guys, any of you do that? 39.1 squared plus 14.1 squared equals, and then we're going to take the square root of that. We're going to get 41.56. Okay. 41.56. You guys good with that? Now, let's compare that. You guys, let's compare that with the actual length that we did when we added it graphically. And when we added it graphically, we got, sorry, is that the right one? Yeah. So we got 10, 20, 30, we got 40. Okay, maybe 40 and a half. Okay, now, I really eyeballed this 45-degree angle, and some people thought it might be 60, right? So we can see that at least it's in the ballpark. And if I really did that carefully by making a 45-degree angle, let's say with a protractor or something, then I'm sure we would have gotten closer. But 40 or 40.5 versus our 41.5 is darn close. Okay, so when you are sketching out these sorts of vectors graphically, and then you connect the, like we did here, connect the where you started to where you ended, okay, and get that length, that can give you a pretty good idea. Now, for the most part, okay, when we have vectors, we are just going to be adding them like this, okay, but usually just 2 and not more than that. And then we will also be talking about how we multiply and divide vectors and that sort of thing. All right, so if this right here, if vector A was 25 and vector B was 20, what would vector A minus vector B equal? So if we now said we wanted vector A minus vector B, okay, then what would that be? Okay, graphically, vector B would just go in the opposite direction, okay? So now, instead of going up and to the right, it's going to go down and to the left. Okay, so this is negative vector B. So now it's going to go down here, and our resultant vector right here, this would be our resultant vector right there. Okay, so let's measure that, okay, and that would be about 19. Okay, well, how do we make this? Now we already did the math here. How do we make this vector B negative? Okay, and all we have to do, okay, is just change the signs. Okay, so now we're going to have minus 14.1 and minus 14.1. Okay, so when you have a negative vector, the signs on both the I and the j just switch. So if this was a plus minus, then it would be minus plus. Okay, now we're going to have 25 minus 14. 25 minus 14 is going to be, what, 10.9? 10.9. And this is going to be negative 14. So this would be our answer in in IJ notation. But if we wanted to calculate the distance there, then we're going to have 10.9 squared plus negative 14.1 squared, which just turns it to be positive. And now, if we do the math there, 10.9 squared plus 14.1 squared whoops, wrong, squared and that would be the square root of 17.8. Okay, so this would be equal to 17.8. And now let's go ahead and measure this. And now we are at about 18.5. So 18.5 versus 17.8. Again, we're really close without having really been very precise. Okay, so here's the other issue. Because a vector also has a direction. It also has a direction. So analytically, what direction is this? Okay, well now, analytically, I'm going to slide this over, okay? We are going to have, let's do our resultant. So our original resultant was 39.1, okay? And so if I say inverse tangent of opposite over adjacent, and our opposite is 14.1, and our adjacent was 39.1, okay, then we can get the angle just from trig, and we're going to say inverse tangent of 14.1 divided by 39.1, and that's going to give us 19.8 degrees, okay? So this was 19.8 degrees, right? If we wanted this one, now remember, that was 10.9. So now we're going to say inverse tangent of our opposite, which is we need to make our angle right here. So we went down 14.1 and over 10.9. So our opposite is negative 14.1 and our adjacent is going to be 10.9. So inverse tangent of negative 14.1 divided by 10.9, and we're going to get negative 52, okay? So this angle right there is negative 52 degrees. And does that seem about reasonable? Does that seem about 20 degrees? Does that seem about negative 52 degrees? Okay, probably pretty reasonable. If we took a protractor there, it would probably come out. All right, so because if we break our vectors into resultant vectors, okay, we break them into the x's and y's, okay, then we can add all our x's and add all our y's, but in the case of vectors, it's really i's and j's. You can think of them as x and y's. We add them together, and to get the resultant, then we're just going to turn that into Pythagorean theorem. And then to get our angle for a vector, because we need to split, or the magnitude, which is going to be from Pythagorean theorem, and our direction is going to be inverse tangent. Our direction is going to be inverse tangent. And you guys are going to have lots of practice on this. You guys, this is going to be the lecture on this, but I'm going to give you problems on this next week. So probably on Monday, you'll see an assignment that's going to be dealing with this vector stuff, and then we will be going into chapter 4, which is two-dimensional kinematics, which are the same equations that we did in chapter 2. For example, equation number 2 is V final is equal to V initial plus AT. We're just going to do that in 2 dimensions. So the original equations that we had, those that I break it down into 4, okay, plus these vectors with trig is going to turn into the next chapter, chapter 4. Sound good? All right, so we will end it here.